Welcome to CPE 350, Chapter 7, Binary Mass Diffusion. We're going to be covering the second half of example 15 when we were looking at the transient diffusion of carbon dioxide into beer, and in this example we'll be solving for the particular solution. Previously we non-dimensionalized the governing equation and boundary conditions, so now we're just going to solve that governing differential equation. And to do so, we're going to substitute for that derivative d omega a d eta with the variable u. And this just enables us to access a form of the equation that can be separated. So if we make that change, we're able to separate and integrate the equation, which becomes, just a little bit simpler because it's lower orders of derivative. If we go ahead and do that, all the u terms go to the left-hand side, all the eta terms go to the right-hand side, and we get an expression containing u. We can cancel out the 2's, and then we can exponentiate both sides in order to solve for u directly. And we notice here that e raised to a constant is also in itself a constant, and we're just going to call that constant c1. So after the first integration, this is what we're left with. And now we can replace that derivative that we exchanged for u. And when we do that, we have another first order equation that we can separate and integrate. So again, we separate the omegas on one side, the etas on the other. And we're tempted to integrate that right-hand side. But remember, this is not an manually integratable expression. This is the definition of a Gaussian. So please do not try to just integrate that by writing e to the negative eta 2 over 2 or something. And we get our second constant of integration at this point. So now we're going to use the error function to replace that difficult integral that can't actually be manually integrated. Remembering that the error function is defined as 2 over the square root of pi, the integral of the Gaussian, we can make our solution resemble this if we multiply. We can make our solution for omega a resemble the error function by multiplying through by 1 in as much as we multiply by root pi over 2 times 2 over root pi. And when we do that, we can see quite simply that we pull out a new constant, which we'll call c1 double prime, since we already have a c1 prime, and the term highlighted in yellow is the definition of the error function. So with this simplification, we are ready to apply the boundary conditions and solve for those constants of integration. So our two boundary conditions, non-dimensional form, are on the right-hand side, and we'll plug in the first one, and we know that the error function of infinity is 1, and so we get that the first constant of integration is the negative of the second. We plug in our second boundary condition, and we note that the error function of 0 is just 0. So that gives us the actual value of C2, which is omega a naught. Now we can plug both of these constants back into the equation and get the full solution to our differential equation. And we can rewrite that and now looking at the solution, it doesn't look the same as the one in the course notes. And there's a subtlety here, because in this example, we're calling species A the carbon dioxide, and in the course notes, we call species A the beer. And in fact, it shouldn't matter which term we solve for. The expressions should be the same for beer and for carbon dioxide. So to double check that we've done this correctly, we're going to go ahead and change this concentration profile into the concentration profile of species B, which is in our case the beer, and see if it looks the same as what we've previously determined. So to switch to omega B, we just use the mass conservation, the fact that in a binary system there's only two species, and so 1 minus the mass fraction of A is by definition the mass fraction of B. So if we subtract our expression for omega A from 1, that gives us an expression for the mass fraction omega B. We can multiply out that omega A naught term, and in order to make this look like the course notes, we also need to make the further change that omega B naught is just going to be 1 minus omega A naught, or vice versa. So we substitute in for omega A naught in order to get it in terms of all the B mass fractions. And when we do that, we have a little bit of algebra. We'll multiply through by the negative sign on the left-hand side. And when we do that, we see that 2 of the 1's cancel, and we're left with an expression that actually does collapse onto the same form as we determined for the beer in the course notes. So now we have the expression for the concentration profile of the beer, as well as the concentration profile of carbon dioxide, and we know that they are complementary to one another in as much as at any given point in space and time, Thanks for listening, and I'll see you for Chapter 8.